Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. So we are going to continue with our chapter on pipeline processor design. There are few problems that could happen in a pipeline processor, and they are called hazards. I think you might have covered this in your digital system fundamentals course, but here we are going to discuss it in a bit more details. Okay. So there are three hazards. Number one is the structural hazard. Then we have data hazard, and third is control hazard. So what is structural hazard? This is a resource conflict. Two instructions may require the same resource in the same cycle. So in that situation, structural hazards occurred. Data hazards are actually data dependencies. So one instruction needs data which has not been produced by another instruction. And in control hazards, it means that decisions about the next instruction needs more cycles. Okay, so let's see what this all means. So you remember the horizontal presentation? We have our instructions on the vertical axis, okay, and we have time on x-axis. T represents the clock cycles, so this is the first cycle, second cycle, and so on. In the first cycle, uh, we have the instruction fetch of the first instruction followed by instruction decode, then execution and memory access and write back for the first instruction. The second instruction comes in during the second cycle. Uh, Whenever the first instruction is being decoded, the second instruction has already been fetched. So this is what we mean by a pipeline, and it follows the same pattern for the rest of the instructions. Okay, in the structural hazard, it is about the resource conflict, means two instructions requires the same resource in the same cycle. This is a very serious hazard and it cannot be ignored. There are two solutions. One is to delay the access to the particular resource that is being contested. But note that the CPI will no longer be one, it will be more than one. The other solution is to add more hardware resources, but that will be more expensive. So those are the two solutions. Here again, it's talking about the solution one to delay all write backs to the register file to stage 5. So ALU instructions bypass stage 4 memory without doing anything. So like this, we can add a delay. And the second solution is to add more hardware resources to resolve it. Redesign the register file to have two write ports because in the current single cycle and pipeline designs, we have two read ports and one write port. So first port is used to write back ALU registered in stage 4, and the second write port is used to write back load data in stage 5. So this is how we can do it. But take note that there is no structural hazards in the present design. Then which we are covering in this course. Because we are using the single cycle data path as our base, so we don't have the problem for the pipeline design. We have separate instruction and data memories, so there is no conflict for the memory part. We have separate adder for PC increment and offset addition with the ALU itself. So each instruction use the ALU in one cycle. So we don't use the ALU in two different cycles for one instruction. Also, one instruction can read from the register, and while another instruction writes into it in the same cycle. So we have no conflict with the register file. So there are no structural hazards in the structure which we are covering in this course. The second hazard is called the data hazards. It is about dependencies of the data. So one instruction needs data which has not yet been produced by another instruction. So let me explain what does it mean. Okay, if you remember the presentation, let's say we have four instructions: load word into $T1, then add using $T1, then we have subtract using $T1, and then set less than, and again $T1 is being used. So we can see that all the same instructions are involving the same register, which is $T1. For the add instruction, its source value depends on $T1, okay, from the first instruction, which is a load word. But notice the value of T1 from the load instruction will only be available at the end of T plus 4 cycle here, okay. However, the add instruction, it needs the $T1 value earlier during the T plus 3 cycle when its ALU operation occurs. So there is a mismatch. The data is needed before it is ready. Okay, so that is called the hazard. Because here in this instruction we need the data here, but it will be ready in this cycle, so it will not be available here. Okay, so the data hazard will occur here. Okay, so we have read after write hazard. Read after write, or RAW, is a part of the data hazards given to instructions I and J, where I comes before J. Let's say I is add $S1, $S2, $S3. So we need to remember how the instruction works. So $S2 plus $S3, and the result is written into $S1. So $S1 is written. Okay. The second instruction is J is subtract $S4, $S1, and $S3. So that means $S1 minus $S3, and the result is written into $S4. Okay, so here $S is being read. So whenever we have this situation where the second instruction reads an integer, a register that the first instruction writes, that is read after write, okay, and the hazards occur when J reads the operand before I has written, okay. So that is when the data hazard happens, okay, because in the read, uh, the hazard occurs because the J reads the operand before I has written it. Okay, so this is the case where hazard happens in read after write. So here is another example. We have subtract $S2, $T1, T3 as the first instruction. Second instruction is add $S4, $S2, $T5. Okay. Third is or $S6, $T3, $S2. Fourth is $S7, $T4, $S2. So we can see that in this program, the execution is in this order from 1 to 5. All the same component is $S2, okay, which is displayed here in red color. So this is the same register which is being used in all the instruction. For the first instruction, the result of $S2 will only be obtained in T plus 4 cycle here, okay, because when it is the subtraction is computed, then in this cycle it will write in the register. So the S2 will be available here, T plus 4. For the second instruction, the result from instruction 1 is required in T plus 2, okay, here. So it needs to read the data here in this T plus 2 cycle, and it need to use it in the T plus 3. Okay, but the data is still not available when it needs. Okay, so for the third instruction, S2 is also being read and required in T plus 3 cycle here. Okay, but the result of the first instruction $2 is only available here in T plus 4. So the result of sub instruction is needed for add or and store word instructions. The and or instructions will read the old values of $S2 from the register file, not the new value being obtained from the subtract instruction, which is performed over here. During the T plus 4, S2 is written at the end of the cycle, so the old value is read. For the and store word, okay, for the and store word instructions, we don't have the problem because the new value is available then for this one, okay, because they are using after this one, so the value will be available. So the only issue will be in these two instructions, okay, because the data will not be available when they need it. See that the result of sub is needed by add or and store word instructions. So the instruction add and or will read old value of $S2 from RF. So during T plus 4, $S2 is written at the end of cycle and old value is read. Okay. So actually it will be available here when the value is available. So in T plus 5, the value will be available. Okay. So how to solve this problem? Okay. So we can solve this problem by having stalls. Okay. Stalls means we put a delay. So 3 stalls during T plus 2 through T plus 4, wasting 3 cycles just to put a delay to make it stop for a while before it continues. So stall cycles delay execution of the add instructions and fetching of it. Okay, fetching of the next one. To add, the add instruction cannot read $S2 until the beginning of T plus 5. So the first instruction executes as normal. The second instruction comes in during the second cycle while it is T plus 1. Then we put 3 stalls, 1, 2, 3. Okay, so these 3 stalls at T plus 2, T plus 3, T plus 4. Okay, then it will continue with the instruction decode for the second instruction in the T plus 5 cycle. Okay, here. Because by this time $S2 value is already available from the first instruction. So we continue the instruction decode here, then the rest of the process continues as normal. For the third instruction, or it will come in during the same cycle where instruction decode for the previous instruction is happening. So here instruction decode for the first instruction, fetch for the third instruction will come in during the same cycle. By doing the stall, the program counter is not modified until the beginning of T plus 5. So what does this mean? That the program counter is not means, it means the next instruction is not going to be fetched. It will only be fetched here in T plus 5. So all these time in these 3 cycles, the next instruction will not be fetched. It will only be fetched here in T plus 5. Please remember, we are going to have your instruction fetch happening during the instruction decode of the previous instruction. Okay, so it needs to be in the same cycle. Okay. Okay, so we have stalls to avoid data hazards. For example, here we have the first instruction as load word $T1 and the second instruction is add $S1 $T1 so on. So we can see that the first instruction writes to $T1, and the second instruction read from $T1. So this is read after write. Okay, same issue. So $T1 will only be available at the end of T plus 4. So we put a stall, two stall cycles. So then we continue with the second instruction. Okay. So basically, what happens that with the stall, it puts a delay which waits, okay, till the availability of the data. Okay, so by adding the stalls, we add a delay, and during those cycles the program counter is not incremented. Okay, and it just keep on the uh, previous instruction. Okay. Okay, so the pipeline stall basically puts a NOP instruction. So NOP, the no operation. The no operation has all the control signal set to 0. It does nothing at execution, memory, and write back stages, so it prevents updates of the program counter and the IFID registers. So the instruction that was stalled is decoded again, and the following instruction is fetched again. One cycle stall allows the memory stage to read data for the load word instruction, and you can subsequently forward them right back to execution. So let's see that how does it work. We have two add instructions here. The first instruction add $T1, okay, means the result of the instruction is going to be written in $T1, and the second instruction is $S1 $T1, where T1 is being read. So this is read after write problem. So if we look at the horizontal presentation, we have instruction fetched, instruction decode, execution, memory access, and write back for the first instruction in the first flow. So the second instruction comes in T plus 1 right below the instruction decode of the first instruction. We can see that the result of $T1 is going to be the written in T plus 4 cycle, okay, here. However, the operation of the first instruction, adding two register, the execution is done during the ALU operation, okay, here. So the result is already available at the end of the execution stage, but it is not written into the $T1 until the write back stage. Okay, so the result that you already obtained from the execution stage can be forwarded to the second instruction in T plus 3 cycle. So this is what forwarding means, okay, that we forward the result from this stage to here. Okay, so this is the forwarding. Another example, we have load word $T1 and the second instruction add $S1 $T1. Again, this is read after write. For the first instruction, the value of $T1 is going to be written in T plus 4 cycle, but the value is uh, being read out from the data memory. So it is actually available at the end of the memory stage. Okay. So in the normal pipeline process, instruction 2 would come in with its instruction fetch, instruction decode, execution, memory access, and write back. So the value that is being read out from the data memory is available at the end of T plus 3. Okay, here. But we need the value of $T1 for the second instruction here in the execution state, which is which is here T plus 3. Okay. So what we do is we stall. We have one stall cycle, then we have instruction decode, and then we forward the value from the memory stage of the load of the execution stage to the add. Okay, so we forward from here to here. Okay. So here is another example. We have add $T1 and then we have store word $T1. This is also read after write. So the actual value of $t1 is going to be written in the write back stage of t plus 4. Okay. The actual value of t1 will be written in the write back stage at here, but the value is already available at the end of the execution stage at t plus 2. Okay, so it can be available over here. So in the second instruction, when the second instruction comes in to the normal pipeline, since the value is already available at the end of t plus 2, so you can just forward it. No store is required. Okay, so it can simply forward it here. The value is needed earlier, so its execution stage at t plus 3 to compute address. But since the add procedure, the value at t plus 2, okay, so the forwarding works directly. So to know when you need a stall or forward and how to forward depends on the instruction. So you need to understand how each instruction works. Okay, so we can see that where a stall is required and delay will work, and where simply the forward can resolve the issue. Here is another example. So we have load word $t1 and then store word $t1. So this is also read after, right? The value of $t from the load instruction is available at the end of t plus 4. Okay, and of the memory stage. Actually, it can be available here as well, but it is written here in the fourth store. So the store instruction needs the value during its memory stage at t plus 4. Okay, to write into the data memory. Since the value is ready by the time the store needs, okay, so we can just forward it directly from the memory stage output to the load to the memory stage into the store. So no store is required here. So we can use it by forwarding itself. The forwarding implementation. So two multiplexers added at the input of A and B registers here. Okay. And data from ALU stage, memory stage, and write back stages fed back. Okay. So it is fed back like this one. Okay. So two signals, control signals, forward A and forward B. So they are used to control the forwarding. Okay, so here is the forwarding unit, okay, which is added in this structure, which controls the forwarding. Okay, to forward it, as mentioned in the previous slides, to forward it, multiplexer are added for the forwarding. Okay, and then after the ALU and write back stages, it fed back to this one, and there are control signals to for the forward A and forward B who manage these forwarding. Okay, so these are the some details for forwarding control signals. If forward A is 0, it means that the first ALU operand comes from the register file. Okay, it means the value of RS. If the forward A is 1, it means the forward result of the previous instruction to A. Okay, so from ALU stage, so it forward back. Then forward, if forward A is 2, so the forward result of second previous instruction to A from memory stage. And if forward A is 3, so forward results of third previous instructions to A from write back stage. Okay, so this is how this four values of forward A are dealt, okay, from the when it's directly coming from the register file, or it is coming from the previous instruction, or the second previous instruction, or the third previous instruction at the relevant stages. Okay, and we got the multiplexers, okay, who decides which, using the control signals, it decides that which value to use. And then we have forward B. So forward B can be 0. So second ALU operand comes from the register file, value of RT. If forward B is 1, it means the forward results of the previous instruction to B from ALU stage. So if forward B is 2, it means the forward result of second previous instruction into B from the memory stage. And if forward B is 3, it means that the forward results of third previous instruction to B from the write back stage. Okay. So you can see that we have this example. Okay, instruction sequences are this: the load word or I subtract, and when subtract instruction is fetched, or I will be ALU stage, so load word will be in the memory stage. So it shows that where forward 2 is needed and where this one is needed based on these explanation. Okay, then we have some raw hazard detection. So the current instruction being decoded is in decode stage. So previous instruction is in the execute stage, and second previous instruction is the memory stage. Third previous instruction is in the write back stage. So okay, so it checks it like this. So if RS is not equal to 0 and RS equals to RD, and it is in the register write situation. Okay, so it shows that at which stage, so what should be the value of forward A and what should be the value of forward B. Okay, so you can read it with reference to this your, as we have seen in this table. Okay, so you can see with reference to the this table that what should be the value of forward A or the forward B. Okay, so here is how it detects the hazard, and it detects. So basically another hazard detection unit is added here. Okay, so which we check the value from each section respectively based on the these all conditions. Okay, so here is the hazard detection and the forwarded unit. Okay, so how these works, so you can see in this one. Okay, so the whole process and their connections are mentioned over here, that how hazard is being detected and forwarded. Okay, and then it is showing that from which component data is flowing accordingly. Okay, here again we have hazard detect, forward, and stall. So everything is combined here. Okay, so it can see that where actually the stall is required, okay, and where forward is required. So it detects the hazard, okay, and then it forward and stalls accordingly. Okay, so this is a complete basically complete diagram, okay, and which involve all the components and this newly added multiplexers and all these components which detects hazards, and where it needs to forward, they use it, and where it need to stall, they do it according to the situation. Okay, so here is a summary of read after write hazard, okay, which we just covered. So given two instructions I and J, where I comes before J. So instruction J will read an operand after it is written by I and called a data dependence in compiler terminology. Okay, so this is called data dependence. So I is add $s1, $s2, $s3. S1 is written, and in the J subtract S4, $s1, $s3, where S1 is read. So hazard occurs when J reads the operand before I writes it. Okay, so this read after write we have already covered in details. Okay. Okay, so what happens if it is write after read? Okay, so what would be problem? So let's say we have instruction J. Okay, that should write its result after it is read by instruction I. So here is an example. We have subtract T4, $T1, $T3. So T1 is read. Okay. So then we have instruction add $T1, $T2, $T3, and T1 is written here. So the component we are looking at second, so the is T1. So basically the common component is this register is T1. Okay, and the second instruction is add this one. Okay, so in this instruction T1 is being written. So read is happened first, and then write is after that. Okay, and where the same register $T1 is being utilized. Okay, so uh, this is write after read. Would that be a problem? Actually, the issue results from the reuse of the name T1. However, this is not a data hazard in the five-stage pipeline because reads are always in stage 2 and writes are always in stage 5. So the read value depends on the previous value, not the value being written later. Since instructions are processed in order, there is no problem. You could also use a different destination register for the add instruction, for example, $15, and then the value, then there is no problem at all. So write after read is not a hazard in this pipeline, okay, because of these reasons that the read are always in the stage 2 in instruction decode, and the writes are always in the stage 5. That's the write back. So instructions are processed in order, so we use a different register to add, for example, $18. So actually write after read is not a problem. Okay, the next scenario. So what happens if write after write happens? So that means the same destination register is written by two instructions. For example, subtract $T1, T4, T3. $T1 is written, and then add $T1, $T2, $3. So $T1 is again written, overwritten it with the new value. Okay, so this is again not a data hazards in five-stage pipeline because all writes are ordered and always take place in stage 5. So there is no problem at all. However, it can be hazard in more complex pipelines if instructions are allowed to complete out of the order. Okay, when instruction J completes and writes to the T1 before instruction I. But normally in the five-stage pipeline, this is not a problem. Okay, so read after read is not a name dependence. Okay, so read after read is not a dependence, so that it's only problem at all. So that is there is also no problem. Okay, so for our current design, the only hazard we need to worry is read after write. Okay, other than that, there is no, either it is write after write, or write after read, or read after read. So there is no header in all these. Okay, so in the pipeline stall, what happens to manage that no operation has all control signals set to 0, so it does nothing at execute memory and write back, and it prevents update of the PC and IFID register. So instruction is decode again, following instruction is fetched again, and once cycle stall allows memory to read data for load word, so it can subsequently forward from write back to execute stage. uh, Showing stall cycles. So stall cycles can be shown on an instruction time diagram. The hazard is detected in the decode stage. So a stall indicates that the instruction is delayed. The instruction fetching is also delayed after a stall. So basically when we need a stall, it always happens right after instruction fetch. So the number of stall cycles depends on the different instruction in the program. The instruction fetch of the next instruction is always in the same cycle as instruction decode of the previous instruction. So it should be right under the instruction decode of the previous instruction. So forwarding depends on the instructions. For a load instruction, the result is available when you read out from data memory. So the forwarding comes from the memory stage. For an add instructions, the result is available when you do the ALU execution. Okay, so the result is available at the end of execution stage. Okay. So it depends on the instruction itself, where the forwarding comes from and how many stalls are required. So it varies from instruction to instruction that it at which clock cycles we need the stall and at which clock cycle we need the forwarding. Okay. Okay. The next hazard is the control hazard. So we have a structural hazard, so no problem is this design. Then we have data hazards, only happens with the read after write operations. And then we have the control hazards. So basically control hazard is the third hazard. So jump and branch instruction can cause great performance loss. A jump instruction only needs the jump target address, and a branch instruction needs two things. First, the branch result to determine whether the branch is taken or not, and second, the branch target address, which is PC plus 4 if the branch is not taken, or PC plus 4 times the immediate value if the branch is taken. Okay, jump and branch targets are computed in the ID stage, at which point a new instruction is already being fetched. So our jump instruction cause a one cycle delay, where a branch instruction causes a two cycle delay, because we need both the target address and the branch result. Okay, here is an example. We have a branch equal instruction BEQ branching to a label. So the branch target address is computed in the ID stage. We are going to actually take the branch in this cycle. So the instruction at the label, which is the target, is shown at I plus 3. Okay, here. So the instruction will be fetched and executed after the branch is resolved. The two instructions fetched immediately after the branch I plus 1 and I plus 2 are one that will squashed or flushed because they are fetched before the branch outcome is known. Okay. Okay, so I think here it will be more clear. Basically, the control logic detects a branch instruction in the second stage. Okay. After fetching the branch instruction, we decode it and recognize that it is a branch. So the ALU computes the branch outcome in the third stage. Okay. So it is computed in the third stage, and the target address is also calculated in the third stage. Next one and next two instructions will be fetched anyways. Let's say that between the branch instruction and the branch target address, there are two instructions, next one and next two. So these are the instructions will be fetched anyways, because while we are decoding that it is a branch instruction and calculating the target address, these two instructions are already being fetched and decoded. Okay, so if the branch is taken, we convert next one and next two into bubbles. Okay, yeah. So that means the rest of the process for next one and next two instruction will be converted into bubbles, and so they with the bubbles, and they will not be executed. Okay, so once we determine that it is going to branch to the target address, the instruction in between are converted into bubbles, and then the operation branches to that target address. Okay, so it will be move to her. So a bubble is again is a no operation, okay, NOP, which is inserted into the pipeline that does nothing at the execution. Okay, so it is almost same like stall. And so they effectively stalling or flushing a stage to prevent incorrect instructions for modifying the processor state. So if the branch is not taken, branches can be predicted to be taken. Okay. If the branch outcome is not taken, then next one and next two can be executed as normal. So do not convert next one and next two into bubbles, and there are no wasted cycles. So the pipeline stages will just operate as usual, just like any other instructions. Okay. So we have the instruction fetch and instruction decode of the instructions, branch instructions. So next is fetch right after the decode of the branch and proceeds throughout the stage normally. Okay. So then next two is fetched right under the decode of next one. Okay, and the rest of the stages will be executed as normal. So this is the internal implementation of branch and jump handling with delay and stalls. Okay, so here you can see that how it is implemented with the branch and the jump. Okay, so here it add the branch delays for those two cycles, and branch target and outcomes are computed in ALU stage at we have see in the earlier slides. Okay. Okay, branch delay can be reduced from two cycles to just one cycle. So branches can be determined earlier in the decode stage. Comparator is used in the decode stage to determine branch decision, which whether the branch is taken or not. So because of forwarding, the delay in the second stage will be increased, and this will also increase the clock cycle. So only one instruction that follows the branch is fetched. If the branch is taken, only one instruction is flushed. So we would insert a bubble after jump or taken branch. So this will convert the next instruction into NOP. Okay. So this is the one cycle instruction. So here we see that it is implemented with the two cycle, but here it one cycle is reduced. So it resets signals, converts next instruction after jump or branch into a bubble. Okay. So this is the main and ALU control, which decides for this one. Okay, instructions come here, and then you are already familiar with all those things. So longer cycle, so data forwarded and then compared. Okay. So this is showing the two cycles for the branch delays. Branch target and outcomes are computed in ALU stage. Okay, so you are familiar with the other components. Okay, okay. So here is another concept which is branch target buffer. So the branch target buffer is implemented as a small cache, so which stores the target address of the recent branch and jumps. So we must also have the prediction bits to predict whether branch are taken or not taken. So the prediction bits are dynamically determined by the hardware. Okay, so it checks over here. Okay, it have a multiplexer with the program counter. Okay, and invented, so it checks over here. So low order bits used as an index. So branch target and prediction buffer, address of recent branch, then the target address, and this is the prediction. So it use it like a buffer. Okay, so that's about the end of this chapter. So pipeline hazard summary. There are three type of pipeline hazards: structural hazards, data hazards, and controlled hazards. So structural hazards, it conflicts using a resource during the same cycle, and as our current structure, there is no structural hazard. So the data hazards due to the data dependencies between the instructions, and the control hazards due to the branch and jump instructions. So hazard limits the performance and complicates the design. In the structural hazards, it eliminate by carefully design or the more hardware. So data hazards are eliminated by forwarding. However, it load delay cannot be eliminated and stalls the pipeline. So delay branching can be solutions when branch delay is one cycle. This completes our topic on pipeline hazards, and also this entire chapter on pipeline processor design. Please do not hesitate to ask if you have any questions before we move to the next chapters. Thank you so much. Assalamu alaikum wa rahmatullahi wa barakatuh.